Good evening, everyone. So today, in the last lecture, we discussed about the equivalent resistances. We discussed about the resistances in series and the resistances in parallel as well, right? So, but today in this lecture, we'll be discussing about Kirchoff's law, right? We'll be discussing about the Kirchoff's current law as well as the Kirchoff's voltage law, right? There are two laws of Kirchoff's. One is the voltage law, another is the current law, right? So let's begin with the Kirchoff's first law. That's the current law, right? So Kirchoff's first law states that total sum of the currents at any junction, right? Junction is a point where two or more than two branches of a circuit meet. That point we call as junction, right? You can see in this picture. Here in this picture, we have point O. This point O is nothing. We call it as junction, right? This is a junction here because here two or more than two branches of a circuit are joining at a common point, and this point we call as junction, right? This point is what we call as junction, right? So in any electric circuit, the point where two or more than two branches of a circuit meet at a common point, we call that point as a junction, right, or node. So Kirchhoff's first law states that the algebraic sum of all the currents at the junction in a circuit is always zero, right? So in a circuit, the algebraic sum of all the currents is always equal to zero. It means that, or we can say that whatever be the current entering the junction, the same amount of current must be leaving the junction as well, right? You can see here in this circuit, we have five resistors, right? These are five resistors, and through each of the resistor, the current is different. The current is I1, I2, I3, I4, and I5. And you can see here that the current I1 here is leaving the junction, the current I2 is entering the junction, and the current I3 is once again entering the junction. Current I4 is entering the junction, and current I5 is leaving the junction, right? So it means that current enter the junction or current leave the junction, but the total algebraic sum of all the currents must be equal to zero, right? Must be equal to zero. We can say that summation of I from n equal to 1 to n, that should be equal to zero, right? That should be equal to zero. That's Kirchhoff's first law, right? All the currents that enter or leave the junction must be equal, right? Whatever the current enters the junction, same amount of current must leave the junction. That's what we call as Kirchhoff's first law, right? Or the current law. Sometimes we call it, in short, we call it as KCL. That's Kirchhoff's current law, right? So there are certain sign conventions that we'll be using with respect to the KCL. The conventions will be like whatever the current entering the junction will be taken as negative and the current leaving the junction will be taken as positive, right? So the three currents, or we can say three currents are entering the junction here, I2, I3, and I4. We'll take these three currents with the negative sign, right? And the current leaving the junction will be I5 and I1, and these two currents will be taken as positive. Or we can say that so I1 and I5 are leaving the junction, right? So we can write here, convention is that current entering a junction, will be taken as positive, right? Will be taken as negative, and the current leaving the junction, right? Leaving a junction will be taken as positive, right? So you can see here that there are two currents. One is the I1, another is the I5 current. These two currents are leaving the junction. We'll be taking these two currents, I1 and I5, as positive, and rest of the currents which are entering the junction, point O, right? We'll be taking those currents as negative, right? So we can write the sum of currents. I2 will be taken as negative, we'll take it as minus I2, and I3 also as minus I3, and I4 also as minus I4, and then we'll be taking I5 and I1 is positive, right? Plus I1 plus I5, right? That should be equal to 0, right? This is the algebraic sum of all these currents, that's equal to 0, right? Or we can say that whatever be the current entering, the current entering is actually the I1, I2, I3, I4. We can write it as I1 plus I5, right? That's equal to I2 plus I3 plus I4, right? I4. So what is this I1 and I5? It's nothing. It's the current leaving. It's the current leaving a junction, right? And what is this I2 plus I3 plus I4? This is current entering a junction, right? Current entering a junction. So there are two statements of the same law. One statement is that either the algebraic sum of the total currents at the junction is equal to 0, or we can say whatever the current is entering a junction, the same amount of current must be leaving the junction. It means that if at this point of junction the current entering is leaving the is equal to the current leaving the junction, it means that actually what happens is that there is no charge, right? There is no charge which actually resides at this point, right? We can say that actually at this junction no charge resides. No charge resides. If no charge resides at this junction, no charge resides at junction, it means that the total charge is conserved, right? Total charge is conserved. So it is only possible if no charge resides at the junction, then the charge entering will be equal to the charge leaving, or we can say that current entering the junction will be equal to the current leaving the junction. And that's why we say that total charge is conserved. Total charge is conserved, right? Total charge is conserved. So it means that KCL or the first law, Kirchoff's first law or the Kirchoff's current law states that total algebraic sum of currents equal to 0. It means that it signifies the conservation of the charge. It signifies the conservation of the charge, right? So KCL signifies conservation of charge, right? Signifies law of conservation of charge. Law of conservation of total charge, right? Law of conservation of charge, because at the junction no charge actually resides at the point of junction. Whatever with the charge entering the junction, same amount of charge must leave the junction, right? So this was all about the Kirchoff's first law, what we also call as Kirchoff's current law or junction law sometimes, right? So let's try to apply this the same. It's a very simple and very straightforward law, right? Let's try to understand more concretely this law with the help of this example, right? You can see in this picture, in this diagram, that we have a question that calculate the values of currents I1, I2, I3, and I4 in the sections of network shown in figure. You can see there's a network given here. There are different resistors in this network and different currents are flowing through different resistors in this network, right? So what we'll be doing is that we'll be using a Kirchhoff's current law to find the current in different resistors, right? In different resistors. So let's begin with from the point A. Let's begin with from the point A. So point A, here's the junction, right? Why do we call it a junction? Because you can see that at point A there are three branches. There are three branches. This is the first branch, this is the second branch, right? And this is the third branch. So at this point A, the three branches of the circuit meet at this single point. That's why we call it as junction. So at this junction, the conservation of charge must be valid, or it must follow the conservation of charge, or we can say it must follow the Kirchhoff's current law, right? So you can see here there are one current is entering, right? The 15 ampere is entering the junction, right? And if 15 ampere is the only current which is entering the junction, right? There are two currents which are leaving the junction. The current is I2 here, right? The current is I2 here, which is leaving the junction, correct? And the third current which is leaving the junction is that's equal to 8 amperes, right? You can see that there are two currents. One is this current, that's the I2, which is flowing through this resistor, and the second current is 8 amperes, which is flowing through this resistor, right? So it means that whatever with the current entering the junction must be the current leaving the junction. It means that if the 8 ampere of current is entering this resistor, is leaving through this resistor, then the remaining current, that's 15 minus 8, that's equal to 7 amperes of current. So it means the current that must be flowing through this resistor must be equal to 7 amperes, because the total current entering the junction was 15 amperes and the 8 ampere is leaving through this resistor. Then the remaining 7 ampere current must leave through this resistor, right? So we can say that this is the 7 ampere current, right? This is the 7 ampere current. Now let's look at this junction, right? Now let's look at this junction. So it's now clear that the current flowing through this resistor, is nothing. It's equal to 7 amperes, right? It's equal to 7 amperes. So it means now at this point, now 3 ampere of current is coming from this right side, right resistor, right? So this is the 3 ampere current from right hand side, right? And this is the 7 ampere current from the left hand side, and both the currents are entering the junction, right? Both the currents are entering the junction. Even if we apply the Kirchoffs current law at this point, it means these 7 ampere and 3 ampere currents are entering the junction. It will be taken as negative, minus 7 minus 3, and the current leaving this junction is the current I3. We can take this current I3 as positive, and that will be equal to 0. It means that the current I3 has to be equal to 10 amperes, right? It means that if 10 amperes of current is entering the junction, the 10 amperes of the current must leave the junction. It means that the current I3 has to be 10 amperes, right? Current I3 has to be 10 amperes, correct? Now let's look at this junction D here, right? Let's look at this junction D. Now at this junction D, you can see that 8 ampere current is entering the junction D here, and the 5 amperes of current is leaving the junction D. Now, how much current is I4 now, right? We can apply KCL at D. KCL at D. If we apply KCL at D, the current entering the D point D here is 8 amperes, right? We can write that as 8 minus 8, right? And the current leaving is I4 and 5 amperes. So we can write it as plus 5 plus I4. That should be equal to 0, right? It means that I4 has to be equal to 3 amperes, right? The current actually flowing through this, that the current I4 is nothing. It's equal to 4 amperes, right? Sorry, 3 amperes. It's equal to 3 amperes, right? So 3 amperes current. So now let's look at this junction C here. Junction C here. At this junction C, you can see 3 amperes of current is entering this junction C, and 10 amperes is 10 ampere current is entering also at the junction C. So if we apply KCL at C, the current entering is 3 ampere and 10 ampere. So it will be minus 3 minus 10, and the current leaving must be equal to I1, right? So it's a leaving current, we'll take it as positive. So that has to be equal to 0, right? So it means that I1 is equal to 13 amperes. I1 is equal to 13 amperes. So from here, we concluded that we applied the junction law or the KCL at different points at different junctions, right? So from there, we concluded that I1 has to be equal to 13 amperes, right? 13 amperes, and I2 has to be equal to 7 amperes, right? And I3 has to be equal to 10 amperes, right? And the I4 is 3 amperes, right? So these are the different values of the current flowing through this circuit, right? Flowing through this circuit. So that's how we apply the Kirchoff's junction law or the Kirchoff's current law, that the total current at the junction must be equal to 0, or we can say that the current entering the junction must be equal to the current leaving the junction, right? Now let's move on to the next question here. The next question is, once again, you can see that figure shows 3 resistances are connected with the switch S, right? Initially the switch is open. When the switch S is closed, find the current passing through it. It means we have to find the current passing through the switch, right? We have to find the current passing through the switch. And this resistor has been given as 2 ohm resistor, right? This is a 4 ohm resistor here, and this is once again a 2 ohm resistor, right? And the potential at this point P has been given as plus 5 volts, and potential at A is given as plus 20 volts, right? Now we can once again to find the current through this switch S, the current has to be calculated through this 2 ohm resistor, right? Whatever be the current flowing through this 2 ohm resistor, right, same will be the current flowing through this switch S, right? If we calculate the current through this 2 ohm resistor, we'll be able to calculate the current through switch S. And we know that here it's a grounded, right? It's grounded. If it is grounded, it means its potential here is equal to 0, right? Potential here is equal to 0, right? For the ground, the potential has to be taken equal to 0, right? So what we can do is that to find the current through this switch, if we know the potential at this point, then we'll be able to know the potential difference between this end and this end. Then we'll be able to calculate the current through this 2 ohm resistor, or we'll be able to find the current through this switch as well, right? So let's try to find this potential first, right? Let's try to find this potential first, right? So V is the potential here, right? Let me assume that at this point, at this junction, V is the potential, right? So V is nothing. V is equal to potential at junction. Potential at junction. Let me call this junction as point D, right? D, potential at D, right? Potential at D. Now, what we'll be doing is that now apply KCL at D. We'll be applying KCL at D. KCL at D. If we apply the KCL at D, so total current has to be equal to 0. So the total current will be, so this is a 20 volt here. Let me assume that this junction is at higher potential. I am assuming here that this junction is at higher potential. So the total current will be V minus 20. That's 20, right? Over the resistance, that's 2 ohm. This will be the current, right? And similarly, it will be V minus 5 over 4 ohm, right? And plus V minus 0 over the resistance here is 2 ohm, right? It will be 2 ohm, right? That should be equal to 0, right? That should be equal to 0. So this is the KCL at this point T, right? So from here, what we can calculate? We can calculate is T. Sorry, potential at point T, right? So it means that 2V minus 20 over 2 plus V minus 5 over 4. That has to be equal to 0. Or we can say that it will be 2V minus 20, right? It will be equal to, just a minute, it will be equal to 4V minus 40 plus V minus 5. That will be equal to 0, right? That will be equal to 0. So it means that 4V plus 5 plus V will be 5V, right? So it means 5V minus 45 will be equal to 0. Or we can say that V is nothing, it's equal to 9 volts, right? It's equal to 9 volts. If V is equal to 9 volts, it means that actually V is at the lower potential than the rest of the points, right? But it doesn't matter, right? So V is equal to 9 volts. So V is equal to 9 volts here, plus 9 volts is the potential at this point, right? V is at a potential of 9 volts, right? At a potential of 9 volts, correct? If V is at a potential of 9 volts, it means that we got to know about the potential at this point. Now the potential difference between this point and this point has to be equal to 9 volts, right? Because this point is at 0 potential, right? This point is equal to is at 0 potential. This point is at 9 volt potential. Then the potential difference delta V is also equal to 9 volts, right? And the current through this will be I. That will be nothing. That will be equal to 9 over 2. That has to be equal to 4.5 amperes, right? So 4.5 amperes will be the current actually flowing through this switch when the switch is closed, right? When the switch is closed, the current flowing through the switch will be 4.5 amperes, right? What we did is we just applied the KCL at this point D, right? And from there we calculate the potential at this point D, and we know the potential at this ground, that's equal to 0. We got to know about the potential difference between the two ends of this resistor, and then we applied the Ohm's law to calculate the current, right? So let's move on to the next law, what we call as Kirchoff's second law, right? Kirchoff's second law. So once again, Kirchoff's second law, what does it state? It's applied in a loop, right? It's applied in a loop, right? So whenever there is a mesh or loop in a circuit, we can apply the Kirchoff's second law, and it says that in a loop or in a mesh, right, the total voltage, the algebraic sum of the total EMF, or the algebraic sum of the total potential drops in the circuit is equal to 0, right? The algebraic sum of the total potential drops is equal to 0. That's the Kirchhoff's law. So in a loop, right? In a loop or mesh, what we do is that we apply the Kirchhoff's second law, which states that the total algebraic sum of all the potential drops of all the potential drops, right, has to be equal to 0, right? So it means that you can see that here we have a circuit. It's a closed loop, right? It's a closed loop. So we cannot apply the Kirchoff's second law in an open loop. It has to be closed, right? It has to be closed, right? So, so which loop is a closed and which loop is open? It depends upon the circuit, right? So we can see in this circuit, right? We have four resistors here: R1, R2, R3, and R4. And current has been mentioned here, right? Current has been mentioned, and we do not know the direction of the current. We can take any direction as the direction of the current in a circuit, right? To apply the Kirchhoff's second law, and the results will actually tell which what will be the direction of the current in a Kirchhoff's second law, right? So let's assume that we have assumed different currents here in this mesh, right? So through R1, it's I1 current through in this direction, right? In this direction, and through R2, this is the direction of current, right? I2, and through R3, the current is I3, it's in this direction, and through R4, the current is I4, it's in this direction. So these are the directions of the current, right? So what is important in the before applying the Kirchhoff's second law is the sign conventions, right? Before applying the Kirchhoff's second law, we must know about the conventions, how we actually have to apply the Kirchhoff's second law in a circuit or in a loop, right? So the sign convention will be very simple, right? Suppose this is the you can go through any directions, right? You can go through like anti-clockwise, or you can go through in a circuit. If you start from a point, either you go from the in the anti-clockwise direction, or you go through the clockwise direction. So it's completely your choice, right? You can go in any direction, be it clockwise or anti-clockwise, but you have to take care of certain conventions for this second law to apply, right? So the convention is that suppose if you are moving along the direction of a current, if you are moving along the direction of a current, right? Along the direction of a current, right? Along the direction of a current, along the direction of a current, right? Along the direction of a current through resistor, right? Through resistor, along the direction of a current through resistor. The potential drop has to be taken as positive, right? Potential drop is taken as positive, right? Is taken as positive, right? And similarly, along or if you are moving opposite to the direction of current, 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 potential drop has to be taken negative, right? Direction of current, potential, you can use any conventions. This is the convention I follow, right? This is the convention I follow, that opposite to the direction of current, potential drop will be taken as positive. It will be taken as negative, is taken as negative, right? For if you look at books, in different books there are different conventions, but this is the convention I follow, right? Potential current direction of current opposite to the direction of current, potential drop is taken as negative, right? So this will be the sign convention I will be using, right? And one more important convention is that if you are passing through a battery or EMF, right? If you are passing through a battery uh, or EMF, right? So the terminal of the battery, the terminal of a battery faced first, faced first will be used for the convention, will be used for the convention, right? For the convention. It means that let me simplify let me simplify it, right? Let me simplify these conventions. It means that let me just simplify all these conventions for you. Let's suppose this is the resistor, right? This is the resistor, and the current I is flowing here, right? This is the resistor of resistance, right? Current I is flowing. Now if I'm moving in a mesh in this direction, right? If I'm moving in a mesh in this direction, it means I'm moving along the direction of the current here. So I will take this potential drop as plus IR, right? I will take this potential drop as plus IR, right? And similarly, if we are moving uh, if I'm moving in the same direction once again, but the current actually it's flowing in this direction, right? Now it means that the direction in which I'm moving in a closed loop, right, is actually opposite to the direction of the current through the resistor. Then the potential drop I will be taking as, it will be minus IR, right? It will be taken as minus IR, right? Similarly, now if I am passing through a battery or EMF, if I am passing through a battery or EMF, now if I let the potential drop of this battery will be V, right? If I am passing through battery or EMF, right? Battery or EMF, so this is the battery or EMF of E, right? So let's suppose I'm moving in this direction in a circuit, right? So I'm facing the first terminal, I am facing this circuit in this battery is the positive terminal, so I'll be taking it as plus E, right? And similarly, for the same battery, for the same battery, if I'm moving in this direction, right, then the first terminal I'll be facing will be the negative terminal of this battery. Then I will be taking this EMF as minus E, right? So this will be the convention for the batteries I will be using, right, in this circuit, right, in this Kirchoffs second law, right? So whatever terminal you face first in a battery, just take that sign of the EMF, and if you are facing the negative terminal, take negative as the sign of EMF. If you are facing the positive terminal of the EMF, just take the positive sign of the EMF, right? Rest, that's what we'll be using always, right? It's the very simple conventions. Just you just have to remember one thing. If you're facing the first positive terminal of a battery, just take the EMF has to be positive. If you're taking facing the negative terminal of a battery, just take the EMF of a battery to be uh, negative, right? So that's it with respect to the sign conventions, right? So let's apply these sign conventions on this circuit, right? Let's apply these sign conventions on this circuit. So what I be doing is that I will just remove these points here, right? Let's apply directly. Let's apply directly these conventions to this circuit to understand it better, right? The conventions are very simple and very clear, right? So let's apply. So you can see here we have this mesh here, right? And by default, I'm moving in this direction, right? In this direction, it's a clockwise direction, right? I can move in the anti-clockwise direction also, but the or in the clockwise direction also, the results will not change, right? So let's move in the clockwise direction, right? So in this mesh, so if I start from this point, let me start from this point. If I'm moving in this direction, then the first I will face is this battery of EMF A3. Since I'm facing the negative terminal of this battery first, so I will take this EMF as negative A3, right? And the current in this resistor is flowing in this resistor R4 is flowing actually along the same direction along the same direction in which I am moving, right? That means that I will be taking this potential drop across R4 as positive. I will take it as I4 R4 plus I4 R4, right? Now, now I'll reach point A, right? Now at the point A, once again the current is flowing in the same direction in which I am moving in this loop, right? It means that I will once again take this potential drop as positive. It will be plus I1 R1, right? Now through R2, now you can see through R2. Now there are two things, right? It depends upon which current is larger and which current is smaller, right? You can see that, let's suppose that if I1 is greater than I2, right? If I1 is greater than I2, right? So or we can do one thing is that there are two currents flowing through this R2 resistor, two currents flowing. So one current is I1 that's flowing along the direction in which I'm moving, and another current is I2 which is flowing against the direction in which I'm moving. So I will take this as plus I1 R2, right? And the second one as minus I2 R2, right? This is the convention I will follow, right? Because for the second case, for the I2 current flowing through this R2, it's moving opposite to the direction in which I'm moving. So I'll be taking it as negative, right? Now, now we reach at this battery E1, right? I'm facing the positive terminal of this battery. I will just take it as to be positive, right? Now let's move to this resistor R3. Now the current is actually flowing along the same direction in which I am moving. I will take it as positive. That's I3 R3, right? Now we reach to this battery of EMF E2. I am facing the negative terminal of this battery. I'll just take it as negative. That's equal to 0. That's it. That's it. We applied the Kirchhoffs second law for this circuit, right? It's a very simple sign convention, very straightforward sign convention, and you use this sign convention everywhere, right? Don't get confused. just whatever the terminal of a battery you're facing first, just take that sign of the EMF, right? And if you are moving along the direction of a current in a resistor, take the potential drop as positive. If you are moving opposite to the direction of current, take that potential drop across resistor as negative, right? So this is how we apply we have applied the Kirchhoff second law, right? So this is the Kirchhoff second law. So let's try to solve this circuit here, right? The circuit is very simple. Here in this circuit we can see we have n number of we have four resistors here, right? We have four resistors with different potential drops at their ends, right? So the question actually is that we have to find current through 12 ohm resistor. Where to find the current through 12 ohm resistor, right? So the current through 12 ohm resistor will be the potential drop across the 12 ohm resistor upon the resistance of that, right? But we do not know the potential drop about across this resistor, but what we know is the potential of one end of this resistor, but we do not know the potential of another end of this resistor to calculate the potential difference. Let's assume V naught is the potential at this point, right? This is the junction point, right? I'm assuming that V naught is the potential at this point. So what we'll do is that apply KCL, apply KCL at this point O, right? Let's apply KCL at this point O. If we apply the KCL at this point O, so the KCL will be nothing. It will be V naught minus 15 over 12, right? Plus V naught minus 3 over 4, right? Plus V naught minus 2 over 6 plus V naught minus 4 over 8. That has to be equal to 0. So this is the KCL at this point, right? At this junction O, right? Now, what we can do is that we have to just solve this equation, right? We have to just solve this equation. So what we'll be doing is that it will be V naught minus 15 over 12, right? V naught minus 15 over 12. That will be equal to plus 3 V naught minus 9, right? Plus V naught minus 2 over 6 plus V naught minus 4 over 8, right? That has to be equal to 0. Now let's solve these first two terms separately, right? This term and this term, right? So we know that it's V naught plus 3 V naught will be 4 V naught, right? And it will be minus 15 minus 9, that's equal to minus 24 over 12, right? That will be plus V naught minus 2 over 6 plus V naught minus 4 over 8, right? That has to be equal to 0, right? Now, so we'll take the LCM of 12 for these two terms. 12 will be the LCM, right? If 12 is the LCM, we'll be left here with minus 4 V naught 24 plus 2 V naught, right? Minus 4, right? And we'll be left here with my V naught minus 4 over 8, right? That's equal to 0, right? That's equal to 0. That's equal to 0, right? So from here, we'll just simplify it. 4 V naught plus 2 V naught will be 6 V naught, right? Minus 28 over 12. And we're left with V naught minus 4 over 8, right? And the LCM of 12 and 8 is nothing. It's actually 24, right? It's 24. So it means that we will be left with 12 V naught minus 56, right? 12 V naught minus 56. LCM will be 24, right? It will be 24 here, right? And it will be plus 3 V naught minus 12. That has to be equal to 0, right? Now 12 V naught plus 3 V naught will be equal to 15 V naught, right? And minus 56 minus 12, it has to be equal to minus 68, right? Minus 68. It will be equal to minus 68. That will be equal to 0, right? So it means from here, our V naught is nothing. It's 68 over 15, right? 68 over 15. So 68 over 15 will be the potential at this point, right? V naught will be here 68 over 15, right? 68 over 15 will be the potential at this point, volts, right? And if we have to calculate the current through this 12 ohm resistor, so the current will be nothing. It will be equal to, we can just write it 15 minus 68 over 15 divided by the resistance, that's 12 ohm. That will be the current flowing through this 12 ohm resistor, right? So what we did in this circuit is nothing. We just applied the KCL at this junction point O, right? From there we calculate the V naught potential, right? And then we calculate the potential difference, and the potential difference over the resistance of this resistor will be equal to the current flowing through that 12 ohm resistor, right? So that's it. Let's move on to the next question, right? The question here is that in this circuit, you can see that we have a circuit here, right? We have a circuit here, right? In the circuit shown in figure, find the current through the branch BD, right? In this circuit, we can see there are actually two loops here, right? ABD and ABDA or BCDB, right? These are the two loops. So what we can do is that we have to find the current through BD, right? There are two ways to solve this circuit, right? There are two ways actually to solve this circuit. We can just go by the both the methods here, right? We can apply the KCL as well as we can apply the KVL, that's the Kirchoffs voltage law. Let's first start with the KCL, right? Let's apply KCL first. KCL. Now what I am doing here is that I am just taking by reference, I am assuming that this point as ground point, right? I am grounding this point D here. It means the potential at this point has to be equal to 0, right? If the potential at this point is equal to 0, right? So it means the whole potential here will be at this end, that will be equal to 15 volt, right? 15 volt, and at this end it will be equal to 30 volts. It means that I can just write this circuit like this. This circuit will be like this. So this is a 0 volt here, right? So this is 15 volt here, and it is 30 volts here, right? So this is 3 ohm resistor, right? And this is 6 ohm resistor here, and this is once again 3 ohm resistor, right? So now I can apply the KCL here at this junction point, right? At this junction point. Let me assume V is the potential at this point. Applying KCL, what we'll get is that V minus 15 over 6 plus V minus 30 over 3, right? Plus V minus 0 over 3. That's V over 3, right? That's equal to 0, right? That's equal to 0. Now we'll be left with V minus 15 over 6, right? It will be equal to 2V minus 30 over 3. That's equal to 0, right? Or we can write it as V minus 15, taking 6 as LCM, right? It will be 4V minus 60. That will be equal to 0, right? So it means 5V has to be equal to 75, right? Or the potential at this point has to be equal to 75 over 5, right? That will be equal to 15, right? That's equal to 15 volts, right? 15 volts. So 15 volts is the potential at this point. If the 15 volts is the potential at this point, right? 15 volts, right? If 15 volt is the potential at this point, and there is zero potential at this point. If zero is the potential at this point, then it means that the potential difference has to be equal to 15 volts, right? 15 volts. And the current flowing through this 3 ohm resistor or through branch BD will be nothing. It will be equal to potential difference, that's 15, over the resistance, that's 3, that will be equal to 5 amperes, right? That equal to 5 amperes. So this is how we solve this circuit by simplifying the concept here. We just grounded the point D, right? And then applied the KCL at this point B to calculate the potential at point B, and then calculate the potential difference between B and T to calculate the current flowing through branch BD, right? We can also solve this circuit using the KCL, right? Using the KVL. So let's see how we can solve the same circuit using the KVL as well. We can solve the same circuit using the KVL as well, right? Let's solve the same circuit using the KVL, right? So how will you apply the KVL in this circuit? Let's suppose that the current flowing through this branch is I1, right? I1. Let's suppose this is the current I1 flowing through this. So it means that this is the current I1 flowing in this circuit, right? And now once this current I1 reaches this branch here, right? This current will break into two components. One will be the I2 through this, right? And then the left current will be nothing. It will be I1 minus I2. That has to flow through this 3 ohm resistor, Now we have two loops here. Two loops here. This is the loop 1, right? This is the loop 1 and this is the loop 2, right? We can just apply the KVL in this loop. Let's apply the KVL in the clockwise direction in both the loops, right? Clockwise direction in both the loops, right? So we can just apply KVL at loop 1, right? KVL at loop 1. So in loop 1, the KVL will be we are initially facing this 15-volt battery, and the first we'll face the negative terminal of this battery. We'll just write it as -15, right? And then we are moving along the direction of the current here in 6 ohm. We'll write it as 6I1, right? Now here in this case, we are also moving along the direction of the current, that's I1 minus I2. We'll just write it as plus 3 times I1 minus I2, right? That's it. So loop is completed. We'll just put it equal to 0, right? We'll just put it equal to 0. Now let's apply the same KVL in this mesh also, right? In this mesh also, what we can do is that we are firstly facing this resistor, right? We are facing this resistor. Here the current is moving opposite to the direction of in which actually we are moving, right? So it means that we'll just take it as negative, and the current flowing through this is I1 minus I2. We'll take it minus I1 minus I2, right? And the resistance is given as 3 ohm, right? Then we are moving along the direction of this current I2 in 3 ohm resistor. That will be taken as 3 times I2. Then we'll just face the positive terminal of this battery, right? We'll just take as positive. That will be 30 volts, right? That's equal to 0, right? That's equal to 0. So we have two equations here. We can just rearrange these equations. 6I1 plus 3I1 minus 3I2, that's equal to 0, or it will be equal to 9I1, right? 9I1 minus 3I2, that is equal to 15. Let me call this as equation first, right? And similarly here we have minus we have minus so we have here in this equation, right? We have minus 3I1, right? Minus 3I1 plus 3I2, right? And plus 3I2 here, right? Plus 30, that has to be equal to 0, right? So it means that we have 6I2 minus 3I1, that's equal to minus 30, right? That's equal to minus 30, right? Or we can write it as I1 minus 3I1 minus 6I2, that's equal to 30, right? Let me call this equation second, right? Now we have two linear equations, right? 9I1 minus 3I2, that's equal to 15, and this equation, right? What we can do is that we have to just solve this equation. If you multiply this equation on both sides, if you multiply this equation on both sides with if you multiply this equation on both sides with 3, right, what we'll get is 3I1, right, minus 18I2, right? That's equal to 90, right? That's equal to 90, right? And we have this equation 9I1 minus 3I2, that's equal to 15, right? That's equal to 15. Now what you can do is that you just subtract these equations, right? You just subtract these equations. Now these are the two equations here. You just subtract these two linear equations. You will get I2, right? And then you can get value of I1 as well, right? So that's it. How you will proceed with the solution of these KVL equations, right? You just form the two linear equations here and try to solve these two equations. You just subtract these two, you will be left with I2 only, and then ultimately calculate the value I2 and I1. Then the current flowing through this VT will be I1 minus I2, right? So that's how we apply the KVL, right? So let's move on to the next question here, right? So the next question here, this will be the last question for today, right? The question is that find reading of a meter and voltmeter if switch S is open and then switch S is closed, right? So we have to in this circuit we have to find the reading of voltmeter as well as reading of the ammeter, and we know that what ammeter and voltmeter does. Ammeter measures the current flowing through the resistor, right, or through the circuit, and similarly voltmeter calculates the potential drop across any resistor, right? And we know that voltmeter is always connected in parallel, right, to calculate the potential difference, because there should be minimum current flowing through the voltmeter, right? So that there will be utmost accuracy in the measurement of this potential difference. That's why we sometimes say a voltmeter is a device of infinite resistance for ideal voltmeter, right? And similarly for current, for similarly for uh, ampere, for or similarly for ammeter, or we say that the resistance of the ammeter should be minimum, right? Should be minimum so that it does not contribute to the overall resistance of this circuit, right? So emitter does, what does emitter do? It measures the current, and voltmeter measures the potential drop across the resistor. And emitter is connected in series and the voltmeter is connected in parallel, right? So let's try to solve it, right? When the switch S is open, right? If the switch S is open, then the what will be the measurement of ammeter, and then what will be the measurement of voltmeter? We'll just try to see that. So when the switch S is open, right, we can see that there will be no contribution of this line, right? No contribution of this line. In that case, this 2 ohm and 6 ohm resistor will be in series, and this 6 ohm and 2 ohm resistor will be once again equal to in series, right? So it will be 6 plus 2, that will be 8, 6 plus 2, that will be 8, and those 8 and 8 resistors, 8 ohm and 8 ohm resistor will be in parallel to each other, right? Those 8 ohm and 8 ohm resistors will be parallel to each other. It means that these two 8 ohm resistor will give an equivalent of 4 ohm, right? So it means that we can just replace this circuit with 4 ohm, right? Just replace this circuit with 4 ohm here, right? This is the meter here. This is the 4 ohm here, right? This is the 1 ohm here. And this is the meter here. And we have connected a voltmeter here parallel to this 1 ohm resistor, right? The battery here is 20 volts, right? 20 volts, right? So my battery here is 20 volts. It means that 20 volts of current must be flow 20 volts of potential drop is applied by the battery. And now these two resistors are once again in series, right? We'll just write down it as 4 plus 1 5 ohm. Or we can say that the current flowing through this circuit will be equal to ideally speaking, the current through the circuit will be 20 over 5, that will be equal to 4 amperes, right? That will be equal to 4 amperes. If 4 ampere is the current flowing through this circuit, same 4 ampere current will be flowing through this 1 ohm resistor as well. It means the potential drop across this 1 ohm resistor will be, let's call that as V1, that will be 4 into 1, that's equal to 4 volts. It means that 4 volts of potential difference will be measured by this voltmeter, right? It will measure a potential difference of 4 volt, and this ammeter is going to measure the current of 4 amperes, right? So that's when the switch is open, right? Now, when if what if we close this switch S, right? If we close this switch S, then the scenario is going to be quite different, right? Let's see what is going to happen to this circuit, right? What's going to happen to this circuit? What we can do is that when we close this switch S, then the 2 points are now connected, right? It's not open, the 2 points are now connected. You can see that now these 2 points are now connected, right? These 2 points are now connected. It means that if these 2 points are connected, then whatever be the potential at this point, the same potential will be at this point, right? The same potential will be at this point. It means that we can just write this circuit like this. We can just rewrite this circuit like this. So this is how the four resistors will now behave, right? This 2 ohm and this 6 ohm here, right? This 2 ohm and this 6 ohm here, right? And the equivalent of these two resistors, that's 2 ohm and 6 ohm, will be nothing. It will be 6 into 2 over 8, right? That's equal to 3 over 2, right? That's equal to 3 over 2. And equivalent of these two resistors will be once again 3 over 2 ohm, right? That will be equal to 3 over 2 ohm. This is also having an equivalent resistance of 3 over 2 ohm. It means that it means that now we can just write these two equivalents like this. 3 by 2 ohm, right? And 3 by 2 ohm. Now these two are in series, right? It will be nothing. It will be equal to 3 ohm, right? It will be equal to 3 ohm. It means that we can just replace this whole circuit with 3 ohm resistor here, right? we can replace it with the 3 ohm resistor here, right? This is 3 ohm and this is the 1 ohm, right? This is the 1 ohm here. And we're applying the voltmeter here, right? And emitter is also connected here, right? So it means that the current now will be, in this case, the current is once again equal to V. The total resistance will be 4 ampere, 4 ohm, and the potential drop is 20. That's 20 over 4. That's equal to 5 ampere current. It means now the current through the circuit has increased to 5 amperes. Initially, the current was 4 amperes. Now the current is 5 amperes. It means if the current is 5 amperes, then it means that this emitter is going to measure or read the current of 5 amperes, right? If 5 amperes is the current flowing through this, it means that this potential, this voltmeter is going to measure the potential drop of 5 volts, right? So it will measure a potential drop of 5 volts, and the potential and the emitter will measure a current of 5 amperes, right? So that's it with respect to the Kirchoffs law, right? In the next lecture, we'll be discussing where to stop here. In the next lecture, we'll be discussing about the AMF of a battery, right? We'll be discussing different cells and the different combination of the cells, series combination as well as the parallel combination of cells. So that's it for today. Take care and goodbye.